Let's continue with the next in the series of What is a Matrix, presented by My Simple Math. In this section, I'll take up an unconventional way to understand and apply the determinants. Unconventional because this is what I think. It's not generally presented around, nor it's validated for academics. So you'll probably get a new perspective and take it what it is. Alright, so in the past videos we have seen that determinants are algebraic expressions, and also that matrices have a physical relevance, being that the numbers that are right there within the matrix have a physical content. They mean something, and therefore the determinants which are composed of those elements, they must have a physical relevance too. So let's see what it is and try to get a feel for it. I'll also present determinants as a property of the system of linear equations. Property means something that is inherent, that's characteristic of that set of equations, and I'll show if it's possible to apply those determinants to some possible applications, one of them being a utility distribution in a city. And not sure, but maybe we can try to figure out if determinants can measure stability as a property of a system of linear equations. Alright, so in the past I've used this experiment. This is we used to set up this experiment and measured the unknown quantities called the unit measures x, y, and z for known values of water in a glass. So let's kind of reverse the logic and try to figure out how to best use this to show that the determinant is a property. So let me repeat the experiment. 3 glasses of water, previously they were measured yielding unit measures x, y, and z. So now over a period of time the glass is measured again by a combination of these measures. But because of the external factors of a different time, place, or temperature, etc., the number of times AI, BI, and CI comes out to be different. And this is perfectly feasible because you could have you could have slight error introduced into the measurements depending upon the location. How do we represent this in terms of a matrix? Let's put it together. So the original matrix is written here. The original matrix was A1, B1, C1, A2, B2, C2, A3, B3, C3, multiplied by, I haven't shown them here, X, Y, and Z. They would give K1, K2, and K3. K1, K2, K3 being the measures of the glasses of water. Now, over a period of time, there were slight errors introduced into the measurements because of variations, and these slight errors were introduced as epsilon in A1, A2, and A3, as delta in B1, B2, and B3, and as gamma in C1, C2, and C3. Now, why I'm taking this? Because I'm assuming that epsilon is a characteristic of the change of the unit measure because of external factors, and that change in the unit remains constant. Say, for example, it will become too difficult also to get epsilon 1, epsilon 2, epsilon 3 right here. So what I'm trying here to show is that there is an error introduced in the unit measures which causes a change, a slight delta in the unknown quantities A1, A2, A3, and we need to figure out if we can use this to show that the determinants is a property. So what we do is we find out the determinant of the new matrix. The determinant of the new matrix is found out by the same way as we had done previously. Here we do A1 plus epsilon multiplied by the minor, which is right here. Let me change the pen. So A1 plus epsilon multiplied by this minor, and this minor goes as B2 plus delta into C3 plus gamma minus B3 plus delta into C2 plus gamma, written right here. Similarly, we have A2 plus epsilon into B1 plus B1 plus delta into C2 plus gamma into C1 minus C1 plus gamma into B2 plus delta, which is right here. The negative sign because of the minor, and similarly the last one. So we find the determinant of the new matrix. Continuing the simplification of the determinant of the new matrix, I get A1 as B2 into C3 minus B3 into C2. I split these apart, and then I took the delta and the gamma outside of of these matrices of these minors, so that now this becomes A1 plus epsilon into a minor, A2 plus epsilon into another minor, and A3 plus epsilon into the last minor, plus delta into this term right here. Now this term will have to be rearranged. Similarly, gamma into this term. This algebraic equation comes from simplification of the expression given previously. And here we see that this is A1 into a minor, A2 into its corresponding minor, and A3 into its corresponding minor, plus epsilon, delta, and gamma into a similar equation as epsilon minor 1 1 minus or plus minor 2 1, this minus sign is because of the minor, plus M3 1, and so on and so forth. So now you can clearly see that when we can express the equation in terms of minors, and the minors are M11, M21, and M31, with the signs interchanging in the exact order that we had learned the determinants to work. So we are clearly headed towards an expression which should be very, very familiar to us. And that expression is the determinant. So determinant is we find out that the new determinant, or the new variable that we got out of introducing an error into the matrix, was the original determinant plus the sum of these errors, epsilon, gamma, and delta, multiplied by the original determinant. So the change in the system brought about could be expressed in terms of the original determinant, and the sum of the errors also could be effected on the original determinant by either multiplying them, here it's completely multiplication, by multiplying them, and thereby yielding the new determinant. So the original determinant plus some of the errors into original determinant tells me that this determinant is an inherent property of the matrix. It did not change, or it became a characteristic that we could use to make something new, which is, in our case, the new determinant. See, now we know that determinants can be expressed as a property, but let's see a possible application of determinants. Let's take a simple system of water supplied to two homes with different meters and consumptions. So there's this home A and there's this home B. Home A has a meter right here and home B has a meter right here. And these are being supplied by bulk fill, which has a meter also called K. So negative consumption is not allowed. Negative consumption, obviously, you can't have water going from here to here. So it's just coming one way, and it's being used up here in these two homes. The leaks are unknown. Water consumption could also be any number in either of these two homes. Obviously, A cannot be greater than K and B cannot be greater than K. So let me write it down. So A is greater than 0, but it is less than K. Similarly, K is greater than B, but it is and b is greater than 0. In a normal flow pattern, A has a band A plus minus A. So on a normal flow pattern, let's say for example, here is K and A is right here. This is A. But A has a band. In that band, A can go from normal flows, A can go from plus A to minus A. Like it can just go like this somehow. Okay. Similarly for B, B can also have, replace this by B. Let's say B is like this. B can have another one which is plus B. This is plus B and minus B. And B can go like this, somewhat like this. So now the question is, what is the best way to define the system as stable? How would a person right here at K, how would a person at K know that, let me change the pen please. How would a person right here at K with this meter in hand and not knowing much about A and B know that the system is stable, that there are no untoward leaks or that there are no untoward happenings that would cause the system to go unstable? I'm using the stability in a loose term here, but bear with me. I think I couldn't find a better word, and I'm trying to figure out if determinants could be used as a characteristic of this entire system, because the determinant is of a matrix has a property, as we have seen before. If it has a property, then it also is a property of this entire system, and let's see how it behaves. This system of two homes, let's make a table. In that table, what we do is we assume that home A is receiving A and home B is receiving B amounts of water, and we also introduce a running 2x2 determinant. A 2x2 determinant means that we draw a line right here from, let's say, change it to pen. Let's say running determinant would be the determinant of A, B, A, B, which is this determinant. So 2x2, right? So if there were like 3 homes, then I would make a running determinant of 1, 2, and 3 rows and 3 columns. And the running determinant would be the determinant of the 3x3 matrix. The sum of the consumption is right here. A plus B, which is the sum of the consumption, that is the K. And here again for home A plus B, the sum of the consumption is right here. If we take the running determinant, then the running determinant of this one would be 0, whereas the sum of the consumption would be A plus B. So we can say that the determinant is 0 for a stable system. There are no changes in the system, and therefore the determinant is 0. Now let's say on the third day the consumption increases, and the consumption increases to A plus A and B goes to B plus B. If we take the running determinant between days 2 and 3 like this, then the running determinant would be AB minus AB and A into small b minus B into small a, which is AB minus BA right here. And the sum of the consumption would be A plus B plus A plus B. So what I can see here is that there are for large numbers, this value right here, the determinant absolute value, may be much larger than the sum of these numbers. We'll see that when we simulate it, but this is a possibility that instead of measuring this, which is the sum of the total consumption in those two homes, we could have a running determinant right here as AB minus BA. Similarly, let's say if it further increases to 2A and 2B, and when it goes from 2A to 2B, we end up as having 2BA minus 2AB as a determinant right here. 2b multiplied by a minus 2a multiplied by b, and 2b multiplied by small a and 2a multiplied by small b right here. See, the sign of this one is kind of reversed compared to this one. So that is why it is best to take the absolute value of the determinant. I'll show the simulation in the next slide. But if we take the absolute value of this determinant, then the absolute value of this determinant is obviously much bigger than this one as the consumption has increased, and this is also much bigger because this is the absolute value of multiples, and here we are simply adding. So when consumption is changing, the determinant could swing, right? But the absolute value will still be larger than the sums of the change, and determinant would help us track those changes in a faster way. So the summary of this slide is that the determinants are a stronger indicator of a change in a system, and it goes back to stability when it goes back to zero when the system goes back to stability. So let's see, we can simulate this happening for a 3x3 system in the next slide. Let me explain the simulation that I did for 3x3 matrix. So I took the rolling matrix of the consumption, and we have 3 homes now, A1, B1, C1, and the sum total is K. So here's what I did. I took the largest sum of the coefficients of the 3x3 matrix. Let's say this is the 3x3 matrix. The rolling average for the rolling matrix for days 1, 2, and 3 on homes A, B, and C. And I took 15 as the largest number possible or the largest consumption in this. And I ran this all the way from 1 to 3 all the way till 55. I didn't want to show too much data in here, but this is continuously going forward. And all of these numbers are random. Say, for example, I just took a Excel and put random between 1 and 2x of that number. Why I took 2x? Because it was like, let me use a pen, because it was from A to twice of A. So the entire the entire consumption could be between A and 2A, that is double the amount. It could be, I could have taken larger numbers or any numbers like squares or 3 times, but normally you only want to have something that is more realistic, and that realistic is that the consumption just doubled. So the consumption on day 1 right here, I took a random consumption between 1 and 2, and should be 2. I took a random consumption between 2 and 4, and it gave me these numbers. And again, I took a random consumption on day 3 between 3 and 6, and so on and so forth. So the numbers continuously increase between here to here. And from 55 to 110, again, the random consumption I took was between random consumption of 95, 55, 72, and some of these would give me a 235. So once we have these largest sum of the coefficients, then I took the determinant of this matrix. The determinant of this entire matrix came out to be -2. The determinant of the next matrix, 2, 3, and 4, came out to be -56. And the determinants of the next matrix on days 3, 4, and 5 came out to -76. Took the absolute value of those determinants. And let me show you in the next slide. I plotted these absolute determinants against the number of days, or against the number of days, or the amount, right? And I also plotted the largest sum of the coefficients, that is this total amount, this random total amount, against the number of days. So I plotted these two. Why I'm doing this is to simulate our previous thought that determinant right here could be used as a measure for change in the system instead of just measuring the total amount that was being consumed in a system. So let's see how the graph looks like. So I plotted the absolute value of the determinant of the 3 by 3 matrix, which was shown earlier in the previous table, and it was made by random numbers between 1x and 2x of that number, say between the consumption A and consumption 2A, or double of that consumption. So I took the random values and I plotted them here. The y-axis right here is logarithmic. That was to incorporate the steep rise of the determinant with the consumption. So this consumption and the number of days are the same. That is, this is A is equal to 10, A is equal to 20, A is equal to 30, and so on and so forth. And I plotted them. This blue line right here is the sum of all the consumptions. So between 10 and 20, I took a random number and then added them all together. So this number comes out to right about 70, approximately right here. Three numbers between 10 and 20. Similarly, three numbers between, let's say, 11 and 22 for this number 11 right here. And I calculated the determinant of the 3 by 3 matrix, plotted it, the absolute value in this golden line, and I plotted the sum total of the values on this blue line. So this sum total of the values is the consumption, and here is the determinant. So you can see that as the randomly distributed consumption is increasing, as the values here continues to increase, the value of the determinant, or the absolute value of the determinant, increases at a faster rate than the value of the sum total of the consumptions. This ties in with our initial assumption that the determinant is a quicker indicator to distribution within the system. But you would also agree that it's too responsive. Say, for example, a change between, let's say this is 15, between 15 and 30, we picked up three numbers and summed them. The sum total right here came out to less than 10, and there's a very small change right here. But see, the determinant just went wild. So the determinant is too responsive as a characteristic of the system. If you want to measure it, then it becomes kind of unwieldy for a control system, or for even people to respond in such small measures, such small changes. The determinant just changed wild, changing by almost 100 times right here. So wild swings of the determinant may make the control unfeasible, but compared to this, it's more responsive. It has got a faster rate, and that's it. It's just a characteristic that we could probably use at a different location. In addition, the determinant can go down to 0. The determinant can go down here, it's 1, but the determinant can go down to 0 even when all the values are positive. So in summary, I've shown that the determinants have a physical relevance. I showed that the determinants are an inherent property of the system, and used a possible application of a determinant to a system to assess the change in the system as a whole. Thank you.